It's okay.
Okay. Well, it's 1 minute after the hour. Um, so I guess we'll go ahead and start with introductions. Today, we're fortunate to have Momme for the Air-Sea Fluxes from Space webinar series. Momme's going to talk about the particle in cell for efficient swell Pickles model. His title is Towards a Particle in Cell Wave Model and Coupled Climate Models. And Momme is currently an assistant scientist at Woods Hole Oceanographic Institution. He was a PhD student at Scripps. He did postdocs at Brown and at NCAR, and he's been thinking hard about waves and how to represent them. So I'll let you take it away, Momme.
Yeah, thanks, Sarah. Sorry for the people who showed up last time, and I didn't show up because I messed up time zones. I was at an NCAR office and whatever. I moved the times incorrectly, but I'm glad that you're here today. In the background, you should see a video of CSM high res. This is a 10th kilometer ocean simulation and a core-degree atmosphere. And you see here all these beautiful eddies in the ocean. And I really wonder how we deal with waves in these simulations because they're currently not in these high-resolution simulations in any of these kilometer scale runs. So that's why I put this talk together and present this alternative wave model for system models. I'm doing this with a bunch of my collaborators, Baylor, Bertrand, Adrian Webb was also involved, and Alex Auger in some capacity as well. Okay, and people start to think about scale when they talk about air-sea interaction, and this is adapted from a white paper about the sub-mesoscale, but I name it now air-sea interaction of the mesoscale. And you see here the atmosphere on top, the ocean on the bottom, and then you see a log spatial scale in the horizontal axis. And we order here the process by the common names we use. So the mesoscale and the synoptic scale, and then the submesoscale in the ocean. And I'm talking about this orange area here, this orange range of scales where somehow the synoptic scale and the mesoscale in the atmosphere are interacting with phenomena mainly at the air-sea interface, like with phenomena of the same scale for surface waves. Yeah, so we're focusing here on mesoscale and submesoscale interaction, even though this is really thought of smaller scales as well later, but I can't show that yet. Okay, to understand this, the talk is 4 parts. First of all, I'm talking a bit about wave generation and non-equilibrium seas and how I used to see them. Then I talk about sea state dependent air-sea coupling in our system models, how we should model surface waves and eddy resolving scales, and then about particle and cell. Okay, how do we make waves or how do we think about that? Well, there's the classic story of waves blowing offshore, right? There's the shore and winds blowing to the left. And the longer the fetches for a given wind speed U10, you create a wave spectrum that you see on the left, right? The wave spectrum grows in total energy, but also the peak wave number goes to the left, like it means the waves get longer. There's a whole like machinery in these wave spectra, right? You can name different parts of the spectrum by specific dynamic ranges. And then there's an underlying idea from Phillips and Klaus Hassemann and others from that time where you think about that there's some fraction of energy input in the equilibrium range. Most of its energy is dissipated in the ocean directly, and only some small fraction goes to swell generation, right? And that goes through like the so-called spectral transfer or wave-wave interaction to longer waves. The problem is now that if you look at like wind observations in the open ocean, you see this, right? This is Antarctica, and you see here surface stress from a high-resolution model output, and you see storms running around Antarctica, and they're everything but constant, nor stationary, right? And the question is really what kind of wave variability these wind patterns generate. And you can model that with wave models, and you see that on the right. So you see here two variables at the same time. The contours are significant wave height, and you can guess that's roughly where the storm is. And the shading is the peak period of the waves, and you see there's a more complicated pattern under that. So are these waves and the winds, like depending on the left or on the right, are they actually ever in equilibrium? Well, there is a theoretical limit of the Pearson-Moskowitz limit, which is like a paper from, I think, the 60s, which is this blue line. So the idea of wave growth under fetch is the following, right? You have a fetch, this is a non-dimensional length scale. The longer the surface exposed to the winds, you grow energy, that's the vertical axis, and then this growing of energy is this tilted line. However, there's a point in the non-dimensional fetch where waves don't grow anymore. They're just a function of wind speed alone because that's the only variable that's left. And that's the second line here in this piecewise equation. You can equate these two things, and then you can back out a wind speed. You can back out a wind speed for it. You can back out this. You can back out the scale for a given wind speed. That's what I mean. So and this is the first out of two arguments why winds and waves are actually nearly never in equilibrium. So if you look at what the Pearson-Moskowitz limit is, that's the black line here, for a given wind speed, let's say 10 meter, a 10 meter wind speed, then the Pearson-Moskowitz limit is somewhere at 500 kilometers. And everything above this line is a so-called fully developed sea, right, where winds forget the length of the fetch, and everything below this line is still a growing sea, where you have this dynamic equilibrium where waves still grow. These two blue things here now are decorrelation scales, either from ocean station Papa, that's this blue dot, that's about 50 kilometers. Does it make? Yes. And then in the Southern Ocean, we have longer ranges that go from about 100 to 1,000 kilometers. Now, this is, of course, sensitive to how you calculate that. This is from error 5. There's questions about that, but I think what I try to make here, the point I try to make here is like this Pearson-Moskowitz limit in the storms is probably more a thing in the Southern Ocean. This argument has to be extended a bit more, but I didn't have time to do it. That's the reason why I give you another one, which is this more like object-based argument. And there I invite you to go on this like extratropical storm. You have the low pressure system and you have a cold front, and the highest winds are normally somewhere behind the cold front, right? And now you're an observer that sits at this red dot, and you travel with the storm velocity big V. And then you think about how the waves around you develop in this moving system. And you can simulate that. One second. That means, right, you will see here a red dot appearing. That's you, the observer. And this thing makes waves as it goes to the right. Now play the video while I close the window. So what you saw is, I play it again, right? You make waves, so winds appearing, and the fetch length is this red bar around the red dot. This thing moves to the right. You create waves, and then the waves decay again because storms have a finite time, and the swell propagates away, right? It goes here, it goes ahead of the storm. The lower level is the peak period. It's not that interesting here, but that's the main process, right? And you can summarize this process in the following. This is from a paper I wrote, now it's about 4 years ago. And this blob you saw is this blob here, and this is a space-time diagram. So if you go upward, you increase in times, like in a Hofmüller sense. And the red line is a red dot. That means you're sitting here in the moving system of the storm. And these curves here are characteristic curves of wave growth. The color is just for illustration. And the idea is here that first the waves are small and slow. That means in the moving system, they're far behind the storm, right? They go to the left. But as they're exposed to more and more winds in this gray area, they get faster. So that means they're bent up in this moving system until the situation here where they continue to grow and then converge and overlap up to here. And you can actually classify these different regimes as the following. So this classic wave growth is here, young C, where the winds are static and the waves are static, but both are dynamically grow. Then you have a growing C where the winds are strongest, and these curves, these characteristic curves are bending and they spatially converge. That's when it's normally, of course, that like the wave group velocity is the same speed as the storm. And then you have an old C where wave growth still happening through this spatial convergence of wave energy, right? The longer waves running in the shorter waves from the same system, but the winds are decaying, right? The winds are not that strong anymore. And then you finally have here the situation of swell, right? At some point, this whole process of wave generation ends. The nonlinear terms decay, you have linear waves, and then you have swell. That's somewhere away from the highest wind speed. So what this model, this idealized wave growth model under moving storms says you that there's a displacement between the strongest winds, which are here in the center, the strongest nonlinear C, which is probably here, and the place where swell should originate, right? And I'm pondering around this because this is basically the first, right? This is the next order model after the static model, what a wave model should reproduce to create dynamic wave generation, right? And that's basically my lowest order benchmark. And we will reproduce that later in the second half of the talk. Okay, what I try to give you here, two arguments, how the synoptic scale of the atmosphere creates something like a non-local filter in the surface winds and therefore for the ocean perturbation, right? I talked about wind forcing that make waves and the waves propagate and so on. And these things are more complicated than just the static fetch relation. The ocean can do the same, right? There's eddy killing and so on, but I'm not talking about that either. Okay, second part. Sea state dependent RC coupling mainly, right? And this is thought about from the modeling perspective. So here we go now back in this box model. This is an ocean model, grid box, and this is an atmospheric model, grid points. And we think about these coupled bond layer systems, there are fluxes between through the RC interface. And you do calculate these fluxes through like the flux formulas, fine. And these formulas should really depend on the 2D wave spectrum, right? That's what you would think of because they determine, like the waves themselves determine how the exchange between atmosphere and ocean. But we probably can get away with like wind-based parameterizations where they are sufficient because the waves don't have a strong impact. But in some cases, we probably need a wave-based parameterization, right? And that's tricky to tease out and really depends on the process. But we should really get a modeling infrastructure that can do that. A case where the wind-based parameterization seem to be fine is Stokes is like the mixed layer parameterization based on Stokes drift from Lee and Fox-Kemper that's here applied in like CMAP class low resolution models. You see here, you observe mixed layer depth based on Argo in the winter hemispheres. These are both winter hemispheres. And then you see here a control run from CSM2 without the Langmuir parameterization for the mixed layer. You can improve that by making theory waves, which is a Stokes drift parameterization. So the waves induce Stokes drift at the surface, which is just a function of U10. And they utilize here the Pearson-Moskowitz limit to do that, right? And you see they get an improvement of the mixed layer depth by about 30%, right? It looks the mixed layer depth here on the lower right look way better at the stuff in the upper left. Now, if you look at the literature of all other RC interaction processes, you actually see there's a growing demand for this infrastructure to test wave-based parameterizations, right? So I'm showing you here two examples. One is SWOT, right? SWOT is flying now, and you see here the mass in dots. This is an airborne measurements, like there's a LiDAR measurements that fly over the ocean surface. And you see here small scale variability in wave height. This is right in HS, in significant wave height. So these are a few tens of kilometers, and that's something which we haven't observed before, only like in incidences, But we have now mass observations of these like small square gradients in HS that are definitely coupled to the currents. So, and then the other one is like this never-ending problem of the marginal ice zone. That's this orange area here. That's the area of the CS that is affected by waves. When waves can break ice, you can invoke very nonlinear processes. You can change heat fluxes between atmosphere and ocean a lot. And we do not model this well in CNAM class models. Then now I'm showing you a table, which someone should never do in a presentation, but this was the easiest way to make a comprehensive summary. So if you list all the processes I could find for that are short dependent on wave processes, so there's some in the atmosphere, in the ocean, and the marginal ice zone, and you think about how these, like what parameters they are based, then you can classify this basically in two groups, right? Most of them depend on moment-based metrics, right? Everything in the atmosphere is normally parameterized through significant wave height, peak period, group velocity, and the like, or maybe steepness. And these can be all functions of moment-based metrics, which is like the spectral moment is defined in the upper right. So if you have an idea of the spectrum, of the spectral shape, you can calculate these higher order moments, right? And in this case, the spectral shape is parameterized. And then there's this other class of parameterizations. For example, wave current interaction or wave breaking through spectra that somehow need the full 2D spectrum or the full 1D spectrum. And that would be computationally more expensive because they say we are very frequency dependent, and therefore we have to model the complete spectrum to get the impact on the climate system correct. But for now, I'm assuming that we can always find a way. So this is basically a call out to the people who work on these frequency dependent processes, that we can always find a way to find a moment-based metric even on eddy resolving models, right? We want to have the statistical impact of these processes, but I hope we don't have to resolve them explicitly. Okay, part 3, how should we model surface waves in Earth system models then? So what we currently do is we solve the wave action equation, which is this 5-dimensional thing, right? Wave action is the wave energy divided by the frequency, and this is a very high-dimensional quantity, and you need to discretize that. That means in every spatial grid point, for example, there, you discretize a frequency interaction, and in each of these black dots, you solve this equation on the left, right? And that's a high state vector, and that's the main problem of these models. They are developed for 30 years. They're very skillful in wave prediction, but the problem is there's an information imbalance, I would say, right? So while my spectral wave model is on the right, and it carries information on each of these black dots at each time step, the information this model comprehends can be properly compressed in the wave partitions, which are illustrated by these red dots, right? And you can describe each of these red dots by the peak frequency, the direction, and the total energy. That means I can write down an approximation of my 2D system probably with 6 to 12 variables, right? And this ratio, which is something like 1 to 3%, is the inefficiency of the WaveWatch model, because at all these white places, like where there's no wave energy, there's basically nothing to calculate, even though it's still in the state vector. Okay, that makes problems when you actually put this in Earth system models. This is a so-called weak scaling, that means I'm comparing the computation effort as I grow the computation problem size, right? So the horizontal axis is the resolution of the Earth system model or of the wave model, and the vertical axis is the effort we need per simulated year. And you see here, if I do simple WaveWatch tests, which is this black line, these black dots, you see here it goes like to the upper left, and that's an n log n scaling roughly. That means, right, if I'm going from something like, let's say 1 degree to, let's say, probably it's 1/6 degree, you have to double the computational cost. So each of these horizontal lines is an order of magnitude. Now, what is currently done is they run at NCAR, they run WaveWatch 3 at 2.8 degrees, which is here, in a CSM that has 1/8 degree, that is here, right? So they allow WaveWatch to run at about 1% of the total computation cost of CSM. If you want to run a WaveWatch at the same resolution as the ocean model here, then it would cost about 22%. That's the number here, right? However, if you want to run a WaveWatch on this eddy resolving model, CSM MESA clip, which is a tenth of the degree, that sits upward here, it would cost 130% of that model. It would be more expensive than the whole other Earth system model, right? And that comes out of this n log n scaling behavior of this high dimensional model, right? If you want to have spectral coupling, you add this line here, roughly, because you have to increase the exchange between the models, and then you beyond whatever an Earth system modeler would allow you to do. So, and that's the problem we face, right? We're facing a computational challenge that we have to provide wave information at nearly no computational cost. So, of course, we would then increase complexity of these models, and it's really the question if we gain physical representation from that or not. Now, this is an Odyssey talk, so I put more lines in the same graphic. So there's, for example, SWOT, which gives you information on 2 kilometers of some wave information and currents. And then there's Odyssey to be thought of 5 kilometers, as far as I remember, right? And then you would think of how much, like, Odyssey sits even in smaller scales than our eddy resolving model at CSM. There's other models out there that are already on the scale. And you would guess the computation cost for a wave model that resolved that would be high. There's a more complicated point to make here, right? And the point is that if we acknowledge that Odyssey observes like a turbulent atmospheric boundary layer and a turbulent ocean boundary layer and a wave layer in between, right? Odyssey sits here, right? How do we use this information of these that we probably get from Odyssey to improve our models, right? How do we use this high resolution information? How do we digest it for model improvement, right? First of all, I think we have to better understand the system at 5 kilometers, right? And for that, we have to reassess the assumptions we made in both boundary layers and in the way and how these things are coupled. So that is a greater task for the RC interaction modeling community, so to say. And then I really want a system that can simulate that at that scale, right? And not only simulate, but also evaluate this at this scale. We want to train the model with Odyssey data, and we want to initialize this with the data at that resolution, right? And for all of this, you need a coupled system that is actually feasible to do. Okay, I'm not the only one who had this idea. Klaus Hasselmann had the same idea in this funny paper, Wave Dreams and Visions from 1990, where he thinks wave models should be an integral part of a nerve system model, right? This is this thing here, and there's all other components that are on the left. They are nerve system models. Wave models are lagging behind. Well, we can now write down like requirements for a wave model in future of system models, right? First of all, we want to provide moment-based metrics that are sufficiently accurate for three-way coupling between atmosphere, ocean, and sea ice, right? Then we want to have this computationally feasible, that means computationally cheap, to run in coupled systems, but we don't want to blow it off the chart in fully of system models. We want this to be easily scalable on like unstructured grid on a kilometer scale, right? So the model should have that property. And then we want to learn from remote sensing data because the physics we see there are amazing, but there's a lot of work to do how to actually constrain that. And these constraints are not necessarily the same as a wave prediction model in weather forecast has, right? I don't really care about the wave scale itself. I'm more caring about representing the variability correct. So I'm losing the accuracy constraint here on purpose because I don't think I want to go the spectrum model route. Instead, we present here this alternative wave model, which is pickled, parting itself for efficient swell. And the logo is this pickle that running on a surfboard in the wrong direction. That's an AI-generated logo. And the idea is the following. We trade here accuracy for convenience. We represent the waves in a Lagrangian sense. That means that each ocean grid point that's here, we see the particle and then solve the wave action equation along this particle. And after some while, we remesh these deformed particles back to the ocean grid. Right, and this is we know how to solve the wave action equation along the Lagrangian path, but what is new here that we really do this remeshing exercise in a conservative way, right? Yeah, the idea is it's sufficiently accurate. I explained that. To do this and to have a good computational scaling, we want to minimize particle-particle interaction because that's costly. We write this in Julia because it's probably a smart thing to do. We focus on open ocean waves here because coastal problems are very different. And we want to have a good scaling on GPUs or expected scaling on GPUs as well. So how does this model will fit in the other models? This is a graph of complexity. You start here with 1D models, so like the fetch relations I showed you before, then typical Lagrangian models, and the ones I showed you with these like banded curves. It's an example of that. And then there's a third generation model, which was introduced by the Swarm project in the 80s and 90s. And we sit here somewhere in between, like we also model space, 2D space and time, but we do this in a less complex way. We do this by Lagrangian particles, right? And this is actually the first model who does this, the first model who combines Lagrangian particles with this particle and cell model so that we can still provide Eulerian output. Okay, some stuff about the numerics. We start with the wave action equation. This n is this 5-dimensional quantity. We neglect currents. That lets us get rid of this one part. And then we integrate in wave number space. So we get an information of a small ODE system of log energy, the group velocity vector, and the position. And the right-hand side are essentially parametrizations for energy input, dissipation, coupling, and direction. And these parametrizations have, at the end, a similar style than the ones in WaveWatch. So these are fully parameterized functions. People can work on them and improve them, but the basic model construction is this, right? That means my WinC is now described by these 5 variables: position, the group velocity vector, and the energy, and that's it. And that's my small, like low effort system. What we then have to do is, right, we have to advance, right, we have to initialize the particles at each grid points, and then we advance them, this is this blue line, under given wind forcing for some time, which could be the coupling time step, for example. And then all the particles are deformed, right? They move to some other place and grow wave energy. What we then have to do is we have to map from this point here back to the grid points, to all 4 neighboring points. And we do that by first mapping from Q, from the, this is flipped up. We're first mapping from P, right, this 5-dimensional thing, to energy and momentum. And then once we have the information in energy momentum, we can add them to the corner points. And I'm elaborate that a bit further later. And here's a notation difference that I just see. Yeah, there's some discrepancy between P and Q. Very confusing. Once we have the information back at these grid points, we reset, we map back, and we go back to the advancement. Let me clarify this mapping problem. So, right, the core idea is here that the state actually exists in 2 systems, either in the Lagrangian thing where I have equations, which is P, but we can also rewrite these 3 variables essentially as Q, which is energy and momentum. And these quantities we can add, right? So you can add energy momentum without any harm, but you cannot add group velocity vectors because that doesn't make sense. A 10-meter wave, a wave with a group velocity of 10 meters per second and 12 meters per second is not 22 meters per second, right? It's something in between or something different. And you can circumvent that by going in this space and then you add. The adding is done through this essentially linear spline, this weighted average. That means the point that is the closest to my Lagrangian grid point gets the most energy. That would be this one, and this one gets the partition based on the area equivalent. Okay, now we can test this model, and we test this on the simplest problem, which is the Pearson-Moskowitz limits again. So this is the fetch time in this case, not space. And the red line is this Pearson-Moskowitz line I've introduced before. And the green and blue lines are pickles, while the green one is the fully Lagrangian solution, where you just grow waves along a Lagrangian particle. And the blue one is the one with remeshing. You see both do exactly the same. That means my remeshing is conservative, and it ends up where it should be at the Pearson-Moskowitz limit. You can discuss this difference here. That's a tuning problem of the parameters. I don't worry that much about. You can make the problem more complicated. Here we now grow winds blowing offshore in half of the domain upward, and time goes to the right. That means you start blowing winds here, and then you go to the right, and then you have a static fetch relation, as in my first slide, right? WaveWatch does the same thing, right? You have also a static fetch, but you have this like diffusive edges because you need that for numerical stability in the spectral wave model. While mine doesn't have that yet, right? Mine model is actually under diffusive. We have to add it back. That means we can control it pretty well. Then we can get more complex. So this is the stationary wind thing that rotates. And you see here the wave energy developing and the momentum as well. You can make beautiful fronts that rotate slowly. So yeah, we can go to that part of complexity, but of course there's caveats in this approach. And that is essentially I'm discretizing in wave partition rather than frequency direction, right? I'm gaining some skill in some parts of the problem, and I'm losing some skill in the other one, right? So what I'm losing is I'm losing this general idea of wave-wave interaction, or how these particles in this case interact. And I have to write algorithms for doing that. And that's the way we have to go, right? We have to describe how wave particles interact. In certain cases, for example, when do I decide waves are windsea or when they are swell? How do they superimpose if they're roughly the opposite direction? Can they superimpose or not? And how do we describe more complicated interactions? One way to go is probably a layering system. That means all I've showed you before is just for wave generation in a windsea, but you can also add more, like you can basically copy the whole model and making layers of the model, while the upper layer is the windsea, and the lower layers are then swell system propagating under this windsea. And then it really depends on cases when the windsea direction and the swell direction interact or not, right? And one way to proceed is here explored by a grad student in France I'm working with. He thinks about the swell generation problem only, so he seeds millions of particles at this blob, and then he let them propagate and spread them out, like in this great circle sense. And he does this by like a method called sequential importance resampling, and that can create these like propagating swell fronts that also disperse, right? Because frequency dispersion is another substantial problem of this particle and cell method. Okay, finally, we can think about more complicated cases and think about the physics of interaction again, and as well as the expected performance. So we can reproduce the same like idealized storm that is moving over the surface with pickles, but this is now in a Eulerian space. That means the horizontal axis is space, the vertical is time, and my storm is now tilted, like there's this tilted blob, and the tilt is the speed of the storm as it propagates over the surface. So we are now in an Eulerian system. And if you do that, you can create significant wave height, which is this one, and peak period, which is this one. And you can compare them to WaveWatch, two different versions of WaveWatch with different flags, with different nonlinear terms. And we have basically the same skill in creating this first order response of wave generation under a moving storm, right? You have this swath of swell like behind the storm in all three cases. Mine is a bit too strong. We are missing the right dissipation. Fine. If you look at the group velocity or peak period, they basically look the same. We have also the same scale, right? We can produce the same as one of the WaveWatch cases. But WaveWatch also creates this other energy here where there's actually no energy. So It makes calculations in like where we shouldn't have anything here and specifically here, even though the energy of these waves is neglectable, right? That means, right, it makes computations that we don't need for the coupling. Yeah. Okay, then we can look at one special case, which is the Stokes drift I talked about earlier, and we're looking here at the integrated Stokes drift through the water column, so the Stokes drift transport. And the Stokes drift transport depends mainly on the first moment of the spectrum. So the peak of the spectrum actually, the peak of the wave spectrum actually matters. And you see here between Pickles in the upper left and the two wavewatch systems on the right that they can do roughly the same thing. I have an amplitude bias, I'm too strong, but we can get this displacement of the highest Stokes drift transport away from the highest wind speeds, right? So this is the center of the blob, but this is the place where the highest Stokes drift occurs, right? And this difference is about 300 kilometers or about 10 hours. That's the eddy scale, right? That's in an eddy resolving model. That means it's on the other side of the front, right? And that's where theory waves, which is on the lower left, actually might be of disadvantage, right? So theory waves does also give me a Stokes drift transport, but only as a function of wind speed. It cannot give me like any non-local information from the winds. WaveWatch can do that, and Pickets can do that too, but Pickets does this for a fraction of the cost, as I'll show you in a second, right? But what I'm showing here is that we can recreate the first order dynamics, and the first order dynamics are important or even for Stokes drift in the open ocean. If you care about surface Stokes drift only, then this difference goes away. And I don't show that slide because of time constraints, but then, right, this point collapses back here, and theory waves has a lot of skill, can basically reproduce this what WaveWatch is doing. Okay, how much does this cost? Back to this complicated weak scaling plot. You've seen everything of here before, but now I'm adding Pickles to this, so it's getting more messy. Pickles is in all cases I ran an order of magnitude faster than WaveWatch. So WaveWatch is this line here. I'm doing now the same test with Pickles, which is the blue line. It also has an n-log n scaling, but due to the smaller state vector, it is substantially faster. That means if we would run a Pickles of this complexity now at the same scale as Mesoclip, like at 10 kilometers, we would end up at something like 10% of CSM Mesoclip. We can do that already. So there's this bluish shading here, right? That means we are uncertain about our effort because we have to increase the complexity of the model. That probably comes with the costs. But we also know we can improve the performance further because our memory allocation is inefficient because the programming is done not efficient enough by me in this case. So it's still open how fast we actually be, but we will be certainly faster than WaveWatch for most, yeah, because our state vector is smaller. Finally, there's also WHAM, like EC-WHAM from ECMWF, that is known to be faster than WaveWatch 3, and these are estimates from another paper I found. And we are roughly at the same ballpark already as WHAM. Yeah, but I just put it in there like to throw it in the debate, so to say. Okay. Finally, some outlooks, right? We have to do a lot of physics in the wave model. We have to deal with dispersion, diffusion, and reflection. We have to deal with this multi-layer problem and solve the allocation issue. There's a whole behind the curtain work about how to implement this in CSM because we couple a Julia code into Fortran, right? There's a lot of effort into doing that. And what we at the end want, right, we want to tune this model by doing some automatic learning of the parameters, which I also didn't talk about. But from here, I'm happy to take questions about any of these.
Well, thank you, Momme, and this is great. Questions? And maybe while people are thinking of questions, I'll ask, you mentioned this diffusion question, that WaveWatch has an intrinsic diffusion built in and Pickles does not. What's the right level of diffusion? Is WaveWatch getting it exactly right?
No, I mean they tune it. So there's should be three in WaveWatch. One is just the numerical aspect,
Hmm.
which we have two to some extent. One is a term that probably overcomes the Gauss-Sprenkler effect. That's a problem that, like, because you discretize in direction, when waves propagate along the different frequency bands, the wave stuff spreads out and you get like gaps in your spectrum. And there you probably have to add something for that. And then finally, it's at the end, we have to ask a WaveWatch modeler to give you a good answer, to be honest. There's also like the problem of swell attenuation, right, which is somehow lumped up with the diffusion. And so they tune it in some fashion. I don't know exactly what they do, but it's made that the model reproduces the observations.
Mhm. So there is work to do. You can't just
There's work
say.
to do, and I will have to do the same, to be honest, right?
Mhm.
We will look at like remote sensing based cases and see what the diffusion should be. Everything is, it's a parameterized world. We don't really
Mhm.
resolve that many physics. Uh,
So other questions? I guess I want to ask about operational versus climate modeling uses. So you've presented this in terms of something that could get fed into ZSM, but WaveWatch 3 is run for a lot of operational purposes to try and figure out where there's going to be a storm surge or um, what's the prospect for something as lightweight as pickles? Could it fill in for WaveWatch 3 on operational things, or are you really thinking strictly about the climate modeling scenario?
um, for people who do wave and wind forecast, who do ship routing, there's companies who do that. They're really interested in getting the cost of WaveWatch down because it's
Hmm.
actually like dollars, right? If
Hmm.
you run WaveWatch on a cloud, everything that reduces the effort, uh, yeah, reduces your like makes things cheaper.
Hmm.
But then I have to compete with the same skill as WaveWatch. So and
Hmm.
that's a longer path. Um, I'm have like I talked with Noah, and so how to say? I think it's important for the climate problem and for the long-term weather, for the season prediction problem, where you would think that you want to get the mix layer right. So, right, you want to get the season
Hmm.
mix layer right for the next season and so on, you multi-year prediction, but you don't necessarily care about the swell forecast at the right time, right? And that's where I think pickets can be of use.
Hmm.
Having here the same skill as WaveWatch on the synoptic scale, like for Surfline or whatever, I don't know if we will get there. Because yeah.
It's a good question. Let's see, Benjamin Barr has a hand up.
Hey, Momme, thanks for the talk. Really enjoyed it. Um, so kind of connected to what Sarah said, is there a prospect for kind of using, would pickles contain enough information that we could run pickles on sort of like a seasonal time scale and then use that to initialize a wave model for a short-term forecast? Do you think there's enough, how many nodes will we need? How many points will we need to get enough information for that?
For like it's a regional forecast, like in
So
the
like yeah, if I wanted to do a regional weather forecast and I wanted a wave model that didn't just start from zero energy. I didn't want to spin up my own
yeah,
like WaveWatch 3 model. Would Pickles provide some help for that?
sure. So you could think of like you have a seasonal forecast system that runs pickles in it, and this provides a boundary condition for a nested model at the coast, right? So WaveWatch is better at the coast than I will ever be. They're very good in that. I don't think I will go there. Um, then the question, can I provide the good enough boundary conditions? I hope so. Um, I will uh, will have to provide the right swell conditions, maybe not the right time, but at some point the timing of the storms is anyway like random. Um, but I would have to provide some variability. So in there, yeah, it's more or less the edge case. Um, yeah, it's one step beyond the climate model problem, I think.
Okay. Yeah, it seems really interesting. And, for regional forecasts, a big problem is like where's the remotely generated swell energy coming from? And so if there was some way to get that without doing Wave Watch 3 on a global grid for a couple of weeks or something like that, then that could be, I think, a pretty useful application.
Yes, if you listen carefully, like the model is called particle self-coefficient swell, but I don't modeling swell yet, right? So we do everything but the swell problem, because for propagating it, you first need to generate the waves, um, and then yeah, what we have to solve is the dispersion problem, right? The dispersion in space and in frequency. That's the that's a critical point. When we get that, we're fine.
Thank you.
Other questions? Well, maybe I'll come back and ask about the satellite question. So you mentioned Odyssey, and I have to give you a little point of information that Odyssey is targeted to retrieve winds at 5 kilometer resolution, which is unprecedented. But currents are harder, and we'll probably have random error, so we'll need averaging to something roughly equivalent to 25 kilometer resolution. Although the user can choose what the averaging cells would look like. So you could imagine if you knew currents clustered in a particular way, you could average to draw that out. So with that mixed resolution, does that affect what you might hope to do? Or how you might think about this? You have to think about it.
Odyssey also has swaths, right? So you have
Yeah,
gaps. Right?
you have gaps, but they're wide swaths. It's not like SWAT.
Okay, but you probably like the wind product we have to use is basically something like CCMP
Mm-hmm.
level products, right? So you do some interpolation between whatever you think is right. Um, I think it's still useful for if we ever get to the more statistical view of things, then the currents are fine, right?
Mm-hmm.
Because like currents are very geographic dependent, right? There's western boundary currents and eastern like coast, like there's very different current regimes. And what we need at the end, we need some idea of their intensity, right? Essentially their vorticity and divergence, right? Of
Mm-hmm.
that intensity. And that would be then just a smoother field in a high resolution model.
Mm-hmm.
So you could still run pickles in with Odyssey information only. I think the aspect that I really like about it is the ability to benchmark like model statistics with it on a smaller scale.
Mm-hmm.
So yeah, that's basically it's nearly independent of the wave model problem. But you get high resolution information that the model provides, right? Because 5 kilometers is where whatever the diamond experiment from JPL and NASA are, right? You use them to simulate Odyssey, but you actually don't know how correct they are, right?
Mm-hmm.
How
Yeah,
good the eddy activity is in the ocean and so on.
yeah, yeah. Observations would make a difference. So, and then if there are no other hands, I'll ask one final question, which is that we are anticipating that there will be another decadal survey for Earth observation from space, and there are big questions about what we need to properly observe the air-sea interface. So there are many ways to think about measuring what happens in terms of momentum transfer, wind, waves, currents at the interface. SAR-based systems, really high resolution, coarser resolution, but more global. What do you think are the priorities?
Me personally, so we have SWOT now, right? And SWOT gives us this high resolution, very high resolution information. And I think if you really want to put it into like in Earth prediction sense, like in improved assimilation of data, you interested actually more in the coverage than the detail. So that's my personal take is I think you want to get right, you want to have an idea of how your spectral tail behaves where the model is not resolved anymore. And that's what everything runs down to. And for that, you need high resolution parts. So for that, like whatever, a kilometer scale resolution would be great. But then the question is how do we digest that? How do we derive statistics from that we can benchmark our model? Because the phenomena now are transient, right? You might be able to assimilate where the mesoscale eddy sits, right? You can do that. You can try that with Echo, but you cannot assimilate the sub-mesoscale part. You told me that 3 months ago. So I'm just so what's the point then of always observing the sub-mesoscale if you cannot assimilate that information anyway, right?
Maybe we'll learn to assimilate it.
What?
Maybe we'll learn to assimilate it.
Yes, but it's like, the
It's
question
just
is,
less well behaved.
yeah, and the question is if it matters on the broader scheme of things,
Yeah.
right? You want to have an idea that there is a sub-mesoscale and how it impacts as the interaction and maybe current statistics and maybe wave statistics. But what you really want is you want a global coverage of the stuff that matters for impacting weather, right? If you have a high resolution global coverage of the mesoscale, which might impact storms, as we hope so, then you're better off than having smaller swaths with more detailed information, where you throw away a third of the signal, right? So that's my take. If you want, it's more like an operational based view than a process based view.
Thanks. Any other questions?
Yeah, can I ask one real quick?
Yeah.
Thanks. Thanks, Momme. I just had a question about the particle-particle interactions. I was curious how important that is, and if you end up taking into account wave-wave interactions when you go to regrid, or if that's completely ignored as a function of wave number. I guess really what I'm asking is the momentum a function of wave number, and so you capture wave-wave interactions when you go to your grid, or if they're totally ignored, and how that relates to the particle-particle interactions.
Currently, the momentum is not a function of wave number.
Oh, okay.
Yeah, I'm ignoring. There's no way to show this well. I'm ignoring the wave-wave interaction because the wave-wave interaction does for me two parts. It's baked up in this fetch relations. So as I showed in the first slide, if you do fetch laws like the parametric fetch relations, wave-wave interaction is part of the tune formula by Hasselmann and friends and other people who did that. And then the second part is the interaction of wave partitions. So there's a swell right running there, and then there's wind sitting on top, and these things interact, and you can calculate this interaction for wave-wave interaction in some point. And I don't model that at all. That's for me the particle interaction, which has to be done on this like instantaneous basis each time I remesh, right? Each time I'm doing this adding operation, each time I'm doing the sum here, essentially, I have to decide if I can add to this particle or I have to put it in the swell partition. So
the particle interactions are done totally on the grid, is that right?
Say again?
The particle interactions are taken into account in the gridding process. That's
Only because the particles don't know their neighbors.
okay.
I don't want them to know their neighbors. It's American suburbia. So right, it's very like you can bootstrap in parallel very well. You only know when you regrid. So at
Got it.
this where these green dots, like these green dots go to this thing. So you have to decide what to do. And the smarter I'm there, the better the model will be. You can do this with machine learning in some fashion.
Great. Thank you.
Well, if there are no other questions, we are just about at the end of the hour. Thank you so much for a really engaging talk and discussion. And thanks everyone for joining.
Yeah, thanks for your time.
Next week, we have Nadia Vinogradova-Schiffer, who's going to talk about the next decadal survey. So I urge people to join. I think that discussion may help us figure out what our next planning stages are as a community. Thanks.